Hi, this is the third lesson in waves. See the description of this video. Uh, the links for my other videos are given in the description. Also, by using the playlist of this channel, you can navigate to the required video. For example, I classified or grouped all my 115 videos into different category like lesson on unit 1, past paper discussions on unit 1, lesson on unit 2, past paper discussion on unit 2. Like that, I classified all my videos into different groups. So by using the playlist of this channel, you can navigate to the required video. Okay, so this in this video I will discuss about diffraction of waves. Okay, it's not a big topic. There is no equations related to diffraction in your syllabus, but there are equations actually, but those are not in your syllabus. So what is diffraction of a wave means? Several times they asked that in the past paper. Diffraction means when a wave passes through an aperture or hole or slit, it will spread out. Same way, when a wave meets an obstacle or an object or something on its path, it will spread around the object. This is called diffraction. So whenever they ask to define diffraction, you can say like this: when a wave passes through an aperture or when it meets an obstacle, it will spread out. This behavior or this property of the wave is called diffraction of the wave. During diffraction, the wavelength of the wave remain the same. Before diffraction, after diffraction, there's no change in wavelength. There's no change in frequency of the wave, no change in speed of the wave. So normally this happens in the same medium. So when it travels in a medium, on its way it meets an obstacle, so it will spread around it. So there's no change in speed, no change in wavelength before and after the diffraction. Same way, when it passes through an aperture or hole or slit, it will spread out. So there also no change in frequency, no change in wavelength. Okay, so what's the meaning of diffraction? Means when a wave passes through an aperture or when it meets an obstacle, it will spread out. This behavior of the wave is called diffraction. So what happens when it's spread out? If a parallel wavefront, normally we consider a parallel wavefront. So when a parallel wavefront meets an obstacle, it will become a curved wavefront. That's the reason, maybe I don't know why, some books they say diffraction means bending of wave, but bending of wave is not a good way to say. If you want, you can say bending of wavefronts. Okay, somewhat we can accept bending of wavefronts, because parallel wavefronts, when they meet an obstacle, it will bend. Or when a parallel wavefront passes through a hole or aperture or slit, it bends. But anyway, whenever they ask to define or state what is diffraction means, I don't think it's not good way to say the wave bends. It's better to say spreading out. Spreading of wave when it passes through an aperture or when it meets an obstacle is called diffraction. So in your syllabus, the questions appeared several times in the past papers, all questions based on explaining type questions. So the explaining type questions, mainly focused on comparing the wavelength of the wave and size of the slit when the wave passes through the slit. Or rarely it appeared, this type of question, that is wavelength of the wave and size of the obstacle when the wave meets or encounter with an obstacle. So these are the questions based on comparing the wavelength of the wave and the width of the slit. Based on that, questions came in the past papers, or comparing the wavelength of the wave and the size of the obstacle. So that's a theory, or not a theory, that's the idea you should know to answer the questions in your syllabus related to diffraction. So I'll analyze these things, comparing the wavelength and the slit size of the slit or width of the slit. Separately I'm going to explain. So I'll draw a diagram based on comparing the wavelength and the size of the slit. Okay, Okay, so we'll consider this diagram. This is the microwave transmitter. Assume it's emitting parallel wavefronts. These are metal plates, aluminium plates kept, and this is the slit between the aluminium plates. So it's two-dimensional diagram. So it looks like that. Sorry, it's drawn in one dimension. Actually, aluminium plates means they are like this. These are the two aluminium plates kept between the aluminium plates. There's a slit like this. Two aluminium sheets are kept with a gap. So there's a microwave transmitter kept behind it. So the receivers, two microwave probe receivers are kept at two different positions. So it looks like two sticks. They are not sticks. Actually, they are aluminium sheets. They are aluminium plates, right? Aluminium plates or aluminium sheets. They will block the microwave. A microwave won't pass through these aluminium sheets. Looks like two broken sticks. No, it's actually two plates. Two-dimensional diagram. This is one dimensional. When I draw it comes like this, so don't have a wrong idea they are two sticks. No, they are two plates drawn in one dimension, right? Okay, so there imagine two microwave probe receivers are kept at two different positions. They are connected to two like a milliammeter. So whenever, depending on the intensity of the microwave received by the probe receiver, the reading of the micrometer or millimeter will show the reading. Higher the intensity, the reading will be more, right? Okay, so here the receiver R1 is kept straight in front of the transmitter. This R2, the probe receiver R2, is kept slightly below the edge of the plate. So that means this can't receive any wave directly coming from this one. So it's kept below. That's why I put a red color dotted line. That means the receiver R2 is kept below the edge of the metal plate, right? Okay, so when you keep the size of the or width of the slit much larger than wavelength, you know, in my first lesson I showed the wavefronts and I told this is the wavelength, the distance between the wavefronts, this indicates the wavelength, this is the wavelength. Okay, so here the width of the slit is much larger than the wavelength of the microwave. We are starting the practical like that. We are keeping the two metal aluminium plates such that the gap between the plates is much larger than the wavelength. This gap between the plates, this gap, if I say D, that is much larger than the D, much larger than the wavelength. Okay, so what will happen? R1 will receive the microwave which is directly passing through the slit. R2 won't receive any microwave because the microwave is not much diffracting, not much spreading out. So R2 is not receiving any reading because it's kept below the edge of the plate, this plate, below the edge of that plates R2 is kept, so it won't receive anything. Now, but by keeping R1 at the same position, reduce the width of the slit. Gradually reduce the width of the slit. Like this, you can bring the slit closer and closer. Something like you can bring the slit like this. So bring the slit like this. Always the position of the R2 should be the same. So I can imagine I move this one only this one is moved like this. So I should bring the R1 little down such that it's always in front of the transmitter. So this is the transmitter again, I should draw like this. So when the R1 is kept exactly in front of this one again, what will happen? The reading of the R1 will decrease. For example, when the size of the slit becomes almost equal to wavelength of the microwave, the reading of the R1 compared to the initial position, when the slit size is much larger, compared to that position, where when the slit is reduced further and further, so I should keep the R1 always just in front of the slit like this. So R1 should be kept here like this, connected to the millimeter. So the transmitter is also kept just always in front of these slits, something like this. So the wavefronts, we can reduce the upper part. So the same wavefronts. Okay, so when we keep like this, what will happen? The reading of the R1, when we reduce the size of the slit, we will see that the reading of the R1 will decrease. The reading of the R2, initially it was 0, the reading of the R2, initially it was 0, that will gradually increase. The reading of R1, which was initially maximum when the slit size is much larger than wavelength, the reading of R1 is much higher. Now the R1 reading will decrease. Why this happens? The reason is, now you know, when the size of the slit is reduced, the amount of energy passing through the slit will decrease because the size of the slit is decreasing. So the microwave can't pass through the metal, it can pass only through the gap. The size of the gap is decreasing. The amount of energy released by the transmitter has no change. So the amount of energy passing through the slit is decreasing. Also, what is happening? The amount of slit, the energy passing through the slit is decreasing and it's going to spread out. That we call diffraction. So when it spreads out, the energy which is passing is decreasing. That decreased amount of energy which is passing through the slit is going to spread out. Means the energy received by the intensity, I can use the word intensity, received by R1 will decrease compared to when the slit size was much larger initially. Now reading of the R2 is increasing. Why? Initially there is no diffraction. R2 can't receive any microwave directly from T, the transmitter, because it's blocked, it's kept below the edge. R2 can receive only the diffracted wave. So what happened to R2 reading? R2 reading is increasing because it's getting the diffracted waves. It's getting diffracted waves compared to earlier. So R2 is increasing, R1 is decreasing. The reason for decrease in R1, the amount of energy passing through the slit is decreasing when we reduce the slit size, and that decreased amount of energy which is passing through the slit is going to spread out, so the intensity is decreasing. That's the reason R1 reading is decreasing. R2 reading is increasing because it's receiving now the diffracted wave. Earlier, when the slit size was much larger than wavelength, R2 did not receive any wave, so its reading was initially 0. Okay, so what happened to the balance energy? When the slit size was much larger, almost all the energy emitted by the transmitter directly went and received by the R1. Now what happened to the amount of energy? Only a certain amount of energy is passing through the slit, I told, when I reduce the slit. So what will happen to the balance energy? The balance energy will reflect back. The balance energy will be reflected back by the metal plate. Okay, I hope you understood. So when again I'm telling, when the size of the slit is much larger than the wavelength of the wave emitted, almost all the energy will pass through the slit with very less amount of diffraction or almost no diffraction. That's the reason R1 received higher rate. R1 received almost all the energy emitted by the transmitter, and the meter recorded higher reading. R2 did not record anything. It recorded only 0 because it was not receiving any wave when the slit size was much larger than the wavelength. Now when you are reducing the size of the slit and the slit size becomes almost equal to the wavelength, what happens? The wave that is passing through the slit is going to reduce. Why? The size of the slit is reduced. The amount of energy that can pass through it will decrease. It can't pass through the metal plate. So the amount of energy, the microwave energy passing through the slit is decreasing. That amount of energy which is passing through the slit is reduced and it's going to spread out, diffract a lot. Therefore, the amount of energy, the intensity of the wave received by R1 is decreasing. That's the reason the reading of the R1 is decreasing. Reading of the R2 is increasing when the slit size decreases. The reason earlier R2 did not receive any wave because it is below the edge of the metal plate. Now it's receiving the diffracted wave and the amount of diffraction is significant when the wavelength is almost equal to size of the slit. There is significant diffraction, so R2 is receiving the diffracted wave. That's a reason the reading of the R2, the meter, is increased or increasing. So what will happen to the energy? Only certain amount of energy is passing through the slit, I said. So what will happen to the balance energy emitted by the transmitter? That will be reflected back by the metal plates. Okay, now when you decrease the slit size further, much smaller than, we are reducing the slit size by keeping the R1, R2 at the same position. Means imagine R1 is kept exactly in front of the slit, R2 is just below the slit. By keeping such way, you are reducing the slit size further. What will happen? When you are reducing the slit size further, that means when the size of the slit becomes, I use the D for the slit size, that becomes much smaller than wavelength. What will happen? The amount of energy passing through the slit will further decrease, and that will diffract further. That will spread out more. So what will happen? Both readings will decrease further compared to when they recorded when the slit size is equal to wavelength. Again I am telling, when you reduce the slit size further such that the size of the slit becomes much smaller than wavelength, what happened to the reading of R1 and R2? Both will decrease further. The reason, when the slit size is reduced further, what happens? The amount of energy that can pass through the slit will decrease further, and that little amount of energy that is passing through the slit is going to spread out more. It's going to diffract more. Therefore, the energy that is going to be received by both R1 and R2 will decrease. Intensity of the microwave received by both R1 and R2 will decrease. Therefore, reading of both R1 and R2 now will decrease further. Okay. So what will happen to the amount of wave reflected by the microwave? Yes, reflected by the metal sheet. Yes, the amount of microwave reflected by the metal sheet will increase because it's allowing only little amount of energy through the slit. So most of the energy will be reflected back by the metal plate. Okay, so that's the idea you must know. Okay, so the behavior I explained just now is applicable for any type of wave, not only for microwave. It could be applied for any type of wave, whether it's a sound or water wave or even light, but the wavelength of light is very small. So finding such small slit bit difficult to see the diffraction, but there will be diffraction for light also. But it's better to know this what I explained could be summarized or conclude like this. Better to know this conclusion, that is when the wavelength is much smaller than size of the slit, or size of the slit is much larger than, D is used for slit width. When the size of the slit or slit width is much larger than the wavelength, what will happen? Most of the wave, that is most of the energy, will pass through the slit with very less amount of diffraction. So the amount of curve you draw on the after diffraction is very less. Even if you draw almost straight, that's correct. But the wavelength before and after should be the same. Therefore, the gap between the wavefronts before and after diffraction should be the same, eye level. And there can be little amount of spreading can be shown when the wavelength is much larger than slit size, or the slit size, other way, the slit size is much larger than the wavelength. Also know that only very little amount of wave will be reflected back from the barrier or from the barrier of the slit, because most of the energy or the wave will pass through it. When the slit size is almost equal to wavelength, what happens? There will be significant diffraction. So that means there will be reasonably large amount of diffraction with amount of energy, certain amount of energy is passing through that. But when you compare the amount of energy passing through the slit in this figure 2 and figure 1, this is the second figure. Figure 2, I can say this is figure 3. This is figure 2. This is figure 1 I put here. So compared to figure 1, the diffraction in figure 2 is more. Also, the amount of energy passing through in figure 2, when the size of the slit becomes almost equal to wavelength, the amount of energy passing through the slit will be lower compared to here. If both waves have same intensity, the amount of energy passing through the slit will be lower because slit size has reduced compared to here. So what will happen? The balance energy will be reflected back by the barrier. So here the amount of reflection will be more compared to here. So the amount of diffraction more compared to here. Here is the more diffraction. When the wavelength is almost equal to size of the slit, more diffraction, less amount of energy passed compared to the first diagram. Okay, when we compare this and this, here the wavelength is much larger than slit size. So slit size becomes much smaller than wavelength. What will happen? The amount of energy passing through the slit will be further decreased because slit size has reduced a lot. So the amount of energy passing through the slit will decrease, but diffraction will increase further. So after diffraction, the intensity will be much lower because the amount of energy passing through the slit is reduced because slit size has become smaller, and it's going to spread out more. It's going to diffract more means intensity will be lower. So here the intensity will be lower after passing through it, and the amount of energy already passing through the slit will be less compared to here. So what will happen here? Most of the energy will reflect back in this situation. Most of the energy will reflect back. So remember that when the slit size becomes smaller than the wavelength, much smaller than the wavelength, not small, just smaller, much smaller than the wavelength, most of the energy will reflect back. Less amount of energy will pass through the slit with large amount of diffraction. When the wavelength is almost equal to slit size, there will be energy passing through the slit with significant diffraction. There will be reflection. That reflection will be lower than the reflection here. When the slit size is much larger than wavelength, most of the energy will pass through the slit. Less diffraction, less amount of reflection also. Okay, so this idea is used in microwave oven. These two ideas are used in microwave oven. You know, when we use microwave oven, through the front door there's a glass, we can see inside. Oh, I think there's a question in the past where we can see inside the vessel rotating, the platform rotating, there's a bulb inside. We can see the light, we can see the vessel is rotating, but the microwave won't reach us. Bulb also inside the microwave oven, microwave also inside the oven, but we can receive the light from the bulb which is kept inside the microwave oven. It can reach us, but we won't receive any microwave. How this happens? You know, the wavelength of microwave used in microwave ovens are almost like 12 centimeter. So there you can see the door, front door consists of double layer glass. Between the layer of glass, there is a mesh of wires. There are mesh of wires kept like this. Mesh of wires kept like this. So the size of the gap is much smaller than 1 millimeter. The size of the gap between the mesh of wires much smaller than 1 millimeter. The wavelength of microwave is almost 11 or 12 centimeter used in microwave oven. So there what happens, the size of the slit is much smaller than wavelength of the microwave, much smaller than wavelength of the microwave. So what happens, most of the microwave inside the oven will not come through the slit. They will be reflected back into the oven without coming out. Okay, even if very little amount comes, that will undergo much larger diffraction, so the intensity received by the user will be much lower. But when you think about the light inside the microwave oven, the bulb is there, you can see the light. The wavelength of light is almost something, the wavelength of the visible light is 300 nanometer to 700 nanometer. This is for red color, this is for blue color. So somewhere we can say around 500 nanometer. That means 500 into 10 to the power minus 9 meter. So in centimeters, you know that. So it's going to be 500 into 10 to the power minus 7 centimeters. So that's the wavelength of the visible light. So the wavelength of the visible light is much smaller than the gap or the width of the slit, or width of the slit formed by the mesh of wires. So the wavelength is much smaller. Wavelength is much smaller than size of the gap formed by the mesh of wires. So most of the light will pass through the gap. So we can receive the light which comes from the inner part of the microwave oven. So we will receive the light because wavelength of the light is much smaller than the size of the slits formed by the mesh of wires. But we won't receive the microwave because microwave is 12 centimeter, which is much larger than the size of the slit. So most of the microwave will be reflect back inside the microwave oven. Okay, so related to these ideas, there were questions in the Edexcel past papers, IAL past papers. January 2014, 6PH 0201, that paper, question 14. Okay, so there two graphs are given, like a distribution graphs, like I'm not drawing exactly the same graph. So one graph for male voice and the other one for female voice. The question is about saying how, the word how by a male and female. So the frequency of the wave against the amplitude for male is given a peak at this is frequency, this is amplitude of the sound, this is the amplitude of the sound, this is frequency. This is for male, it's given at almost 300 hertz, almost at 300 hertz. For female, it's given at 1000 hertz, the frequency 1000 hertz. When male and female, when they say the word how, the voice frequency spectrum actually given. There are other peaks also given, but smaller peaks, others are, so we don't need to consider the highest peak, we need to consider. Okay, so the question there, it says first part, peak wavelength for the male is about 1 meter, that's okay. Show that the peak wavelength for the female is about 0.3 meters. Speed of sound in air is given 330 meters. So it's not a big issue. It's O-level type question by using V equal F lambda. We know the frequency is 1000. Speed is given 330 meter per second. So V equal F lambda if you use, you will get the wavelength 0.3 meter for the female voice. Okay, so the B part. It is possible to hear someone talking from the other side of an open door because of diffraction, even when they are not in the line of sight. Describe what is meant by diffraction. Okay, so anyway, what is meant by diffraction I already explained, but How do we hear the sound when someone talks from the other side of the uh, door, but the person is not in the line of visible? Say for example, this is the door width, so this is the size of the door. Maybe you are standing here, the other person might be standing here, so you both of you can't see because there's a wall. This is the door, but you can hear the voice from him. This is you are labeled as X and the other person is Y. So when he says something you can hear, but both of you can't see each other. How is it possible? The sound diffracts through the slit, through the doorway. The sound diffracts. So the voice emitted by the sound emitted by the person Y will pass through the doorway and it will diffract. So the amount of diffraction depends on these conditions. Okay, the amount of diffraction depends on these conditions. Okay, so anyway, B part, first part, describe what is meant by diffraction. You know that when a wave passes through an aperture or when it meets an obstacle, it will spread out. This behavior or this behavior of a wave is called diffraction. So that part is nothing. Okay, my aim of this question is now coming. The second part of that question, it is suggested that a male voice may be heard in this way more effectively than a female voice. So in the question, they are giving it at the start of A part, the peak wavelength for the male voice is 1 meter. So for male voice, they are saying the wavelength is 1 meter. For wavelength of male, I put lambda m 1 meter. For female voice, lambda f 0.3 meters. So the question is, it is suggested that a male voice may be heard in this way. What do you mean by in this way? The previous part they are saying it is possible to hear someone talking from the other side of an open door because of diffraction even when they are not in the line of sight. So it is suggested that a male voice may be heard in this way more effectively. That means diffraction is more effective for male voice than female voice. The reason here they are saying, comment on this suggestion for a doorway of width 90 centimeter. So they are saying there's a doorway. This is the doorway, right? So this is a wall. This is the gap. We normally learn like a gap or slit. Now this is the door. The width of the door here is 90 centimeters. Almost 0.9 meter. Okay, so maybe you are standing here. The person who is saying the word how, that's the way the question is starting. The person who is saying the word how may be standing here. So if this is a male, then the wavelength will be equal to 1 meter. The 1 meter is almost equal to 90 centimeters. So 90 centimeter means 0.9 meter. So the wavelength is almost equal to size of the door width or size of the slit size. Okay, width of the slit is almost equal to wavelength if this is a male. Which diagram is applicable? The second diagram is applicable. So the male voice, when it passes through the doorway, it will have a significant diffraction. I already drew the diagram. It will have a significant diffraction. So the male voice will diffract significantly. So when you stay here, you can hear the voice or the word produced by the male because there will be a significant diffraction. But when you think about female, you won't be able to hear the voice clearly. When she says the word how, if it is a female, if this is a female, the wavelength will be equal to 0.3 meter. They are saying it. 0.3 meter, the door width is 0.9 meter, 90 centimeter. So 0.9 meter or 90 centimeter is the door width. The voice female 0.3 meter given in the question paper. So which diagram is applicable for female? This one. Is it? This one. This one means the wavelength is much smaller than door width. D is the slit size, the 90 centimeter. This is 0.3 meter, 0.9 meter. So 3 times larger. So 3 times larger means the female voice, when it passes through the door width, it won't have diffraction. So it might go something like this, a very less diffraction or maybe almost no diffraction like this. So when you stand here, you won't hear the sound. That's the answer you should say. Okay, so here the answer, just 2 more questions. So you can give the answer. I'm not writing it. You understood, I hope. Male voice has greater wavelength and almost equal to size of the door width. Therefore, there will be significant diffraction. Since the female wavelength is much smaller than the size of the door width, therefore the amount of diffraction will be less through the doorway. Therefore, the person on the other side won't be able to hear the word by the female. Okay, that's the answer. Okay, so another past paper question based on these ideas that appeared during January 2015 WPH 0201 question 17. So there this diagram was given. So it says it's a microwave transmitter, this is a microwave detector, and this is metal plate. As I explained, so the metal plate, there is a gap. So a student is doing a practical, they are saying, so there the question says that the microwave radiation source and the detector are left in the same position. So this and this have no change in the position, while the size of the gap between the metal plates is varied. The output of the detector, so the detector is connected to some output detector, and the size of the gap are measured. The graph shows the results. So on a grid they gave this graph. The detector output again, size of the gap in centimeter. So they are varying the size of the gap. So they plot a graph. So here the graph is starting with, here there is 0. When the size gap is 0, detector reading is 0. When the size also 1, almost 0, then gradually increasing. So there's a peak somewhere at 4 centimeter. When the size of the gap increases further, the reading is decreasing. The question, just it's a 4-mark question. The question is, explain the shape of the graph including an estimate of the wavelength of the microwave radiation used in this experiment. Again I'm reading. Explain the shape of the graph including an estimate of the wavelength of the microwave radiation used. So here actually the given is not a graph, it's just a plot of the reading. So you can draw a basic line. So it comes like 0, 0. So you can draw a basic line, something like this. It goes like this. Anyway, the shape of the graph, you can say increase the detect output, then decrease when the size of the gap increases. They asked to explain the shape of the graph. So already I explained it. So that is given in these 3 diagrams. So starting with gap size 0. Gap size is 0. So the answer I am not writing. I will explain. You can understand. The gap size is 0. That means when the gap size is 0, the detect output is 0. That means there is no gap. That means all the microwave will reflect back. Nothing will be received by the detector. When the gap size is 0, all the microwave will reflect back without passing through the gap, because there is no gap. Therefore, the output of the detector is 0. 1 mark is given for that. Then you should explain about these regions. When the size of the gap increases, or you can explain that after giving these 2 points, when the size of the gap is 0, there is no gap, all the microwave detect reflect back, therefore there is no output, so nothing is detected. So then you can say about when the gap size is much smaller, these points you can explain, this point, this point, this point, those things. When the gap size is much smaller, the microwave that passing through the gap will have large amount of diffraction. So little amount of microwave will pass through the smaller gap, and that will have large amount of diffraction. Therefore, the intensity of the microwave detected by the detector will be lower. That's for the 2nd mark. When the gap size is much smaller, very less amount of microwave will pass through the slit. Most of the microwave will reflect back, and the little amount that is passing through the slit will have large amount of diffraction. It's going to spread a lot. Therefore, the microwave received by the detector will be much weaker. Therefore, the intensity reading is lower. Then you can see when the slit size becomes equal to wavelength of the microwave, there will be significant diffraction, and the reading of the microwave detector will be maximum. And they asked to estimate the wavelength almost equal to 4 centimeter, because we are getting the peak detector output, maximum detector output, when the size of the gap is 4 centimeter. Then the last mark, 4 marks, I already told 3 points. 4 points about this region. Why the reading of the microwave detector is decreasing when the size of the gap is increased beyond 4 centimeter. That is related to this diagram. Then you can see when the size of the gap increased further beyond 4 centimeter, most of the microwave will pass through the slit with less amount of diffraction. Since the detector is kept below the edge of the slit, it won't receive significant amount of diffracted waves. Therefore, the detector output will decrease because amount of diffraction is decreasing. Most of the wave is passing straight through the gap. Therefore, diffraction is decreasing. So, amount of microwave received by the detector is decreasing. That's the reason output is decreasing. Okay, so next thing is about how diffraction happens around an obstacle. How to compare the wavelength of size of the obstacle. Okay, so there, first diagram, there's an obstacle, right? This is the wavelength. So this is the wave, blue color, black color is the obstacle. So here the wavelength, gap between the wavefronts smaller than the height of the or size of the obstacle. So there what happens, the amount of diffraction will be much less. There will be larger shadow region. So the amount of diffraction will be less. Remember the shape of the diagram. So there will be much smaller shadow region, much larger shadow region. Much larger shadow region means the region where there is no wave, that is the shadow. So that will be larger. Now when the wavelength is larger than the size of the obstacle, small obstacle, what happens when the wave passes around the obstacle? So here we take the wavelength is larger than size of the obstacle or almost equal to size of the, both I consider the same situation. So whether it's a larger or almost equal to size of the obstacle, there will be diffraction. So the wave will bend here. So the shadow region where there is no wave, that region will be much smaller compared to here. So that means when the wavelength becomes larger than size of the obstacle, or when the wavelength is almost equal to size of the obstacle, diffraction will be much more around the obstacle. So the shadow region will be smaller. But when the wavelength is smaller than size of the obstacle or the size of the obstacle larger than the wavelength, there will be less diffraction around it. So there will be larger shadow region. Based on that, there is a question, the past paper related to radio transmission, that is January 2011, January 2011, 6PH02, question number 12. Okay, so there the first part is nothing. Radio station broadcasts at a frequency of 198 kilohertz. The first part, 198 kilohertz. And they asked to find the wavelength of the wave. So you know radio waves, the speed is same as all electromagnetic wave, 3 into 10 to the power 8. So by using V equal F lambda, you can find the wavelength. You will get the wavelength almost 1515, I think 1515 you will get it, 1515 meter you will get for the wavelength. Yeah, 1515 meters. So they are giving the frequency 198 kilohertz. The question is find the wavelength V equal F lambda. You will get 1515 meter. The second part, that's the explanation part. Obstacles such as buildings and hills can make it difficult to receive some radio signals with shorter wavelengths. So generally they are saying, explain why this is less for a problem for this radio station. This radio station means the radio station which is transmitting at a wavelength of 1515 meter. For this radio station, it's not a problem. Buildings or hills are not a problem. Explain why, 3-mark question. So there you should say, actually, 1515 meter means there are no buildings taller than 1515 meter. So there the diagram is, this is the diagram. Height of the buildings will be smaller than the wavelength, or wavelength which is 1515 meter will be much larger than height of the buildings. Therefore, there will be larger diffraction around the buildings like this. Wavelength larger than the height of the building. Something like that. Wavelength larger than size of the obstacle. Here the obstacle is the building. Wavelength is larger than height of the building. So there will be larger diffraction around the building. So a radio which is below the height of the building also can receive the diffracted waves, so it won't be a problem. If the wavelength is smaller than height of the building, so the diffraction will be less, there will be larger shadow region. So the radio which is kept below at the bottom of the building or below the height of the building will not receive the diffracted wave. So there the radio will not receive any waves. Here, if the wavelength is larger than height of the building, the radio can receive the diffracted signals. Okay, that's the answer you should tell. Okay, so that's all related to diffraction. So it's not a big topic, but there are questions appeared several times in the past papers. Okay, I hope you understood. So that's the end of diffraction. If you subscribe my channel, you will get the notification when I upload the next lesson. Bye.